Johnny here with Simpson Math, and in this video I'm going to cover improper integrals, how to integrate improper integrals. Alright, to get started, I'd like to integrate from 1 to infinity 1 over x squared. Now, up until this point in the calculus sequence, I've been giving you some integrals that are very nice to integrate. The whole point was teaching you different strategies, different techniques to integrate. Now, we've come across some, though, that they've got some problems. So, in fact, let's take a look at 1 over x squared. So let me see if I can just switch over there. I'm just on desmos.com, and I'm going to type in 1 over x squared, just to take a look at this function. So I've got this red function here, and oh yeah, the larger numbers I plug into the function, the smaller it becomes. So if I plug in 5, the y value there is 1/25. If I plug in 10, I get 1/100. So as I go to infinity, this thing goes to 0. Now I'm looking at this, or I want to integrate it from 1 to infinity. So let me change my domain here. I'm going to say x has got to be bigger than 1. That's all I really care about on this function. All right, so if I kind of forget the negatives, forget that 0, I'm looking here. I'm going to zoom in a little bit so I can get a better picture of what's going on. Oh yeah, starts off at 1, 1, and then it really quickly starts to emulate a horizontal line, y equals 0. So it almost becomes horizontal. Now remember, integration is calculating the area under that curve and the x-axis. So to help demonstrate that, I'm going to try to shade that region that I'm trying to sum up. So let's say I want 0 to be less than y, which is less than that function itself. That works. Oh yeah, so I'm looking at this shaded region, and I'm trying to calculate all of that area. So in the past, if I did from 1 to 3, I could cut off at 3, find that area, add it up, and that would be my sum. I could go from 1 to 25, 1 to 100. The issue with this one is I'm going all the way to infinity and beyond. So I keep adding more and more and more to my sum. So, and your first instinct may be, well, this is just going to blow up. As soon as I add some area to my pot, and I just keep adding area, I just keep adding area forever, then eventually that should just sum up, right? Well, let's play with it. But in my integration process, I have a problem with my infinity. I cannot treat that like a number. I can't go from 1 to 3 and then calculate this. That infinity is going to be a problem with these improper integrals. So the way we handle that is we instead create some dummy variable, and then we use our old friend, the limit, to limit ourselves, to evaluate what's going to happen as I get closer and closer and closer to infinity. All right, what I mean by that is I want to create a limit. I'm going to create a dummy variable. I'll use t. So as t approaches infinity of my integral from 1 to t. So my claim here is infinity, I cannot treat it like a number. So if I'm going to integrate from 1 to infinity, I really need to talk about that as 1 to t, figure out the integral with a t variable, and then later I can worry about that limiting process. I can let t be bigger and bigger and bigger. All right. Now, I can handle this. This is 1 over x squared, or I could think of that as x to the negative second power. In fact, I think I'll do that. Now, this is beginning of calculus, the big struggle there was not, you had to copy the limit notation. We have to keep copying it until we evaluate the limit. So right now I'm just writing my integrand. I like to see my powers as powers. It helps me apply the power rule for integration. So the limit as t is going to infinity of, and I can integrate this. We increase the power by 1, so up to -1, but we multiply out front by the reciprocal of that power. The reciprocal of -1 is -1. And I'm evaluating this thing from 1 to t. So the integration step is over. Now limits have that same linearity aspect that integration does. I can take that -1 out of the limit, just like I could out of an integration. So I'm going to rewrite this as a negative limit as t approaches infinity of, and then I'm going to use the fundamental theorem of calculus to shove in the t, subtract, shove in the 1. And this is just x to the negative first power, or 1 over x. So I'll get there in a second, I guess. I have t to the negative first power minus 1 to the negative first power. I almost dropped my minus sign, but it's there. I'm just going to reciprocate these. This is 1 over t minus 1. I think I'm ready now to evaluate this limit. I've simplified, I've integrated, and I've simplified. Now I'm ready to evaluate the limit. So this is direct substitution. There's a problem, like I can't plug in 0, but this function is continuous out there beyond infinity, so I can, direct substitution is, safe. And we get a negative 1 over infinity minus 1. And when we're in this limiting process, 1 over infinity is such a small number that it's basically 0. So I have a negative 1. Oh, 1. So when I calculate the area under that curve, let me go back and look at that again. I don't believe it. I'm going to make this bigger. Make that bigger. If I take a look at this graph and I keep zooming out, and I add that area, and I keep adding it for as long as I can possibly go. Keep adding area. Come to find out, when I'm done adding, beyond infinity and beyond, it's going to sum up to 1. All that shaded area sums to 1. That's interesting. Okay. When an integral adds up to a number, we say that that integral converges to that number. All that shaded area summed up to 1. I have a lot of students who question me there. They're still blown away. They're like, no, it's got to be more than 1. If you keep adding and you keep adding, like as soon as you get to 1, when you keep adding, shouldn't it still be 1? I mean, it shouldn't be more than 1. My example to students is, I like to show this one. Let's take a number, something like 5. And I'm going to add a number to 5. I'm going to add 0.5. And then I'm going to keep adding. I'm going to add to that number 0.05. So it's a smaller amount. And I'm still adding. And I'm going to add an even smaller amount, and an even smaller amount, and an even smaller amount. And I'm going to continue that process forever. Dot, dot, dot. In the end, when I'm done adding, I should have 5.5 repeated. Just 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5. So that will sum to 5.5 repeated. It won't get any bigger than that. Even though I'm continuously adding bits and bits and bits. It's just that those bits are so small, they don't affect my number. So that's what's happening with that 1. We're getting to, I don't know how to explain it, but they are adding up to 1. All right, let's go through some more of those. And I just used a new word, I think, converges. So because that improper integral did sum up to a number, we say that that integral converges to that number. Well, there are some integrals that don't converge. You can say they don't converge, but another way to say that is they diverge. So if an integral does not converge, if when you add up all that value, all that area, and if it doesn't add up to a number, then it must be just growing and growing. So it's going to be divergent, or it diverges to infinity. If you're calculating negative area, then that maybe diverges to a negative infinity, but it's expanding ever. It doesn't converge. Let's do another example. Something very similar. Let's integrate from 1 to infinity x to the negative first power. This is very similar. This is the 1 over x situation. So the graph looks very similar, especially starting at 1 to infinity. I can get a good little sketch here. I know if I plug in 1, I get 1. But then it does the same thing where it approaches the x-axis. And I'm trying to sum up all that area. Now the previous function, 1 over x squared, approached the x-axis faster than this one does. If I plug in 5, I'm only at a fifth, whereas in the previous function of 5 gave us a 1/25th. So this is approaching 0, but it's a little bit slower. So does that affect this converging, diverging thing? Or when I sum this up, maybe this time it adds up to 10. I don't know. All right. The process. Infinity. It's not a number. I can't treat it like a number. What I'm going to do is introduce a variable, and then because that variable is going to infinity, I'm going to introduce limit notation. I think I'll switch up my variables. I'll do lambda. The limit as lambda approaches infinity of the integral of 1 to lambda of 1 over x dx. All right. Well, I got this. That's just a natural log. This is the limit as lambda goes to infinity of the natural log of x, but I'm supposed to evaluate that from 1 to lambda. I use the fundamental theorem of calculus to do that evaluation. I still have a limit as my dummy variable lambda goes to infinity of the natural log of lambda minus the natural log of 1. Well, the natural log graph looks something like this. I know there's no negatives, even zero, like natural log of 0 is not defined. The natural log of 1 is 0. And the graph does something like this. It's famous for always growing, but at a very slow rate. So this flattens out, but it does always increase. So the natural log of 1, I know that value. It is 0. And I think I'm ready for direct substitutions as well. So I'm just acknowledging natural log of 1 is 0, and then I'm using direct substitution. It's okay to plug in infinity in the natural log. And then the natural log of infinity, because this does increase forever, that is going to be infinity. And infinity minus 0 is infinity. Oh, so this, when I add up the area for 1 over x, the amounts of area that I keep adding are just big enough that the area does increase, and therefore it's increasing forever, and so that area adds up forever to infinity. So we say that this original integral diverges to infinity. All right. Now, those two examples are famous, and they help us illustrate something called the p-test. Previous two examples are particular illustrations of a well-known fact that we call the p-test. It states, suppose you have some a value that is positive, and you're integrating from that a value to infinity of 1 over x to some power. This is what we just did 2 of. Our a in both of those examples was 1. So we had some positive number out to infinity. And we had 1 over x to the first power, and we had 1 over x to the second power. P-test says this will be convergent if that power is bigger than 1. So we did a power of 2, and it did converge. Now the p-test also says this will be divergent if p is less than or equal to 1. We just did the example of p to the first power, and that was divergent. That's the tipping spot. Anything bigger than 1, it would converge. So if I was 1.01, that's enough to make that area so small that it no longer adds up. It just converges to a number. All right, so let's maybe do a quick little example where maybe you're not asked to evaluate the area or to integrate. All you want to know is, will this thing converge or will it diverge? So I'm given this integration problem from 5 to infinity of 7 over x to the 3/2 power. And all I want to know is, if I start adding up that area, will it converge to a number, or is it the situation where it just kind of diverges and I'm going to have infinite area? Okay. Well, the 5 doesn't matter. I just need that a to be a positive number. So the fact that it's 1 versus 5, it doesn't matter. This is a positive number, check mark. The p-test so far seems to be okay. The 7, that's no big deal. That 7 just is pulled out, and it's going to be 7 times whatever that area is. So if the area is 50, well, 7 times 50 is still going to be a finite number. Versus if that p-test gives me an infinity, well, 7 times infinity is still infinity. So the 7 doesn't matter at all. I still have, you can pull it out, so you still have 1 over. In fact, let's just do that real quick. So the 7, you can pull it out, and then I'm applying the p-test to this, which is a positive value to infinity of 1 over x to some power. I'm just looking at the power. 3/2 is bigger than 1. Because the power is bigger than 1, I know that this integral is convergent. I'm going to say that. P is bigger than 1. Therefore, convergent. This is a hint at what is to come next time. We'll be talking in the next video about some comparison tests. And you just want to know, does it converge or does it diverge? But there's 2 good examples that helps clarify the p-test. But let's go back to this improper integral idea. And let's look at another example. I'd like to integrate from 0 to 1 e to the square root of x over the square root of x. So I've been working on strategies for a few weeks now, and I see some good use substitutions, but there's something new here that's scaring me. What is scaring me? Look at this function. I only care about it from 0 to 1. What happens if I plug in 0? Square root of 0, I can't divide by 0. That number is not even defined in my function. There's something going on at 0. I think 1 is okay. So, like I said at the beginning of the video, so far everything I've been giving you has been in fantasy land, all these nice pretty integrals. Moving forward, you've got to concern yourself with what you're integrating. This function seems great and all, but I've got domain problems. I can't plug in negative numbers because that's the square root of negative. That'd be some imaginary stuff. And then, that's okay though, maybe. But for sure I got a problem at 0. I cannot be dividing by 0 and then trying to evaluate this thing from 0 to 1. I can't do that. I'm going to have to use that variable trick again. I'm going to let 0 be some dummy variable, and then I'm going to evaluate the limit as x approaches 0, and in this case I got to be approaching it from the right. So right off the bat, we've got some domain problems. We call this an improper integral. It's not proper in this form because I can't actually do that. So I know how to handle this though. I treat it kind of like it's an infinity. It's a number that I'm interested in, but I can't quite use it. So I'm going to use a variable and then do my best to approach that number. So I'm going to introduce limit notation. I'll introduce a variable. This time I'm going to use omega. So I'm evaluating the limit as omega approaches 0. And I can't come from the negative region. I've got to come from the positive region. So it's a one-sided limit. The integral of that stuff. And, oh yeah, from omega to 1. Now this integral, I think u substitution is going to turn out real nice. If I let u be e to the blah, then the derivative of e to the blah is no wait. If I let, that's not going to work. Let me do the square root though. If I let u equal the square root of x, which is the same thing as x to a 1/2 power, then du, just applying the power rule, I'm going to bring down the power of 1/2, rewrite my base, subtract 1 from that power, and I'm going to rewrite this power. I'm going to kick it down into the denominator and rewrite it as a square root, just to help me see what's going on, make it look like my function. Oh yeah, this is good. That's exactly what I needed. The du will put a square root of x in the denominator. The 2 needs to go away, so I'm going to pull that 2 out. And then I'm ready for some u substitution. Still evaluating the limit as omega approaches 0 from the right of the integral from omega to 1. I probably could pull that 2 out even further. Let me try that. I'm going to put that 2 out of the integration process. Then I'm writing e to the u. Oh, and then that's just going to be a du. Fraction's gone. Wait, one more second. I'm going to do that one more time. E to the u, and then du is this. Nice. All right, I can integrate e to the u. It's simply e to the u. Now that 2 is a constant inside the limit. It can come out of the limit as well. It came out of the integration process. It can come out of the limit process as well. I'm going to integrate e to the u. The integral, oh man, I'm in u land, but I'm using w and 1, and those are x variables. So I should fix that real quick. If x equals 1, then u is the square root of 1, which is just 1. Oh, so that 1 in x land is also 1 in u land. That's nice. Okay, well, if x is omega, then u is the square root of omega. So I do need to change this one. In u land, this is the square root of omega. All right, there's so much going on here. Replace the 0 with an omega. Cool. Replacing the x's with u's. Cool, and then the limits too as well. Okay, I think I'm back on track. Pull the 2 out. Still have the limit. I'm integrating e to the u, which is simply e to the u. But I do need to evaluate that from the square root of w to 1. So I will do just that. Okay, I've integrated, I've simplified as much as possible. E to the 1 is simply e. Now I'm ready for direct substitution. The limit is gone because I'm evaluating it. I have e minus e to the square root of 0. Well, the square root of 0 is 0. E to the 0 power is 1. Oh, I got a number. Like almost 4 or something around there. So this integral does converge. That area does sum up, even though there's something weird going on at 0. There must be some sort of vertical asymptote at 0, and we've got a curve again, and we're trying to add up area. This time, it's going to the y-axis. In fact, I want to see that. We just did it, but I want to see this function in action. I'm going to go back over to Desmos. I'm going to type in this function. I have e being raised to the x. But then I'm dividing that by the square root of x. And I am concerned with 0 to 1. So I'm going to say my domain is from 0 and 1. Less than or equal to 1, I guess. That's a funky looking function. So yeah, this clearly has some area, but then we're trying to add up that area that's hard to show. This little bit in here, this little bit, this little bit, this little bit, this little bit. I mean, it goes all the way up. So you think there'd be this infinite area, but it's that same idea. It gets so skinny up there that you're adding this such a small sliver that it's basically you're not adding enough, and so it converges. Interesting. So instead of adding horizontal area, this is a vertical area. Same idea though. Man, that's some crazy stuff. Okay, let's move on. Let's do another example. Oh yeah, I like this one. Okay, amping up the difficulty level here. Let's tackle this next example, the integral from negative infinity to 0 of x e to the x. Okay, well, right off the bat, I can tell this is going to be improper because of the infinity. And if I want to integrate this thing, looking at the integral, we'll come across all those strategies. I see a product, so I'm thinking integration by parts. Okay, we'll do one step at a time. I'm going to first rewrite my problem. I'll go back to t. The limit as t approaches negative infinity of this integral from t to 0 of x e to the x with respect to x. I'm going to go off to the side and see if I can figure out this integration. That is parts. So I've got an algebraic part and an exponential part. I'm going to let u be the algebraic expression and dv be the exponential expression. Du is then just dx, and v will be the integral, which is just e to the x. That's nice. Parts formula, let me write that down. The integral of u dv equals uv minus the integral of v du. So this will be equal to x e to the x minus a new integral, v, which is e to the x, du, which is dx. And yes, I can integrate that. The integral of e to the x is, we just said, e to the x. I could even pull out an e to the x to factor this. I don't have to worry about a plus c because I'm about to have some limits. Alright, so I went off to the side and I calculated or found the integral of x e to the x. So I'm just going to make that substitution in there. Limit as t approaches negative infinity of e to the x times x minus 1, but I do need to evaluate that integral from t to 0, where t is at negative infinity. All right, I'm ready for that fundamental theorem of calculus. Plug in a 0, plug in a t, and subtract. E to the 0 is 1. 1 times negative 1 is negative 1. Here I have t e to the t minus e to the t, and there's a minus sign in front of both of those. Let me just clean this up. Maybe I should have kept that factored out. I don't know. I'm going to distribute the minus sign. I like this limit because I can separate it. I'm just trying to decide if I want to factor that e to the t out. It doesn't much matter if I plug in a negative infinity. I am going to rewrite this. I wish I had left the e, t factored. So in this next step, I'm going to separate this limit into two limits. Because limits are linear operators, you can do that. So I'm separating this difference. And I'm going to pull that e to the t back out. Like so. Let's see if you like this. The limit, as t approaches negative infinity of negative 1. I want to say minus. Limit as t approaches negative infinity of. Now pull out a minus sign. That's going to make that a minus sign. Pull out an e to the t. Leaves me with t minus 1. Which is what I had to begin with. I just went back to that step. Sorry, I don't know why. I just went back to this step. Okay, I'm ready to do this limit, I think. The limit of a number is going to be that number, no matter how hard you try. Here, I'm plugging in a negative infinity in place of that t. So I am direct substituting. And I'm going to have e to the negative infinity times negative infinity minus 1. Well, negative infinity minus 1 is still down there at negative infinity. E to the negative infinity, I'm going to rewrite that as 1 over e to the positive infinity. Okay, I know that. E to the infinite power is going to be a big number, like infinity and beyond. And 1 over infinity in this limit talk is 0. Oh my god. Do you see what I see? We were dealing with limits, and we came across this product of 0 and negative infinity. Do you remember what we call that in Calculus 1? This is called a product indeterminate, meaning we don't know what that is. The way we handled that back in Cal 1 is we said, you know what? Forget the product. Let's rewrite that as a ratio. A ratio indeterminate we can handle using that L'Hopital's rule. So I'm going to go back to my limit right about here. And I'm going to change this. Instead of looking at it as a product, I'm going to rewrite this as a quotient. And just kind of hope and pray that that works. So that negative 1, I'm not concerned with that at all. No matter what I do, that's going to be negative 1. But I'm now subtracting a new limit as t approaches negative infinity. And I want to take that product and rewrite it as a ratio. I have two options. I could take the t minus 1 and raise it to the negative first power. I think, though, I'll take the e to the t and call that e to the negative t in the denominator position. So I just took the limit that ended up as a product and said I'd rather take that limit and talk about it as a ratio. Now when I try direct substitution, let's see what happens. Plugging in negative infinity, I have neg infin minus 1 up top and e to the negative infinity down below. What's negative 1 minus negative infinity over e to the positive infinity, which is positive infinity. Okay, I got it. Remember this? This is L'Hopital's rule. I put a little asterisk to let me know that I'm going to apply L'Hopital's rule, which means I go back to the limit and I can apply L'Hopital's rule. I need a new sheet of paper here. So yeah, these improper integrals bring back limits, and clearly everything with limits. So all the strategies to break them apart, all the strategies to evaluate them. Okay, now I'm going back to that. And I'm saying we still have that negative 1. The little h over the equal symbol means we're applying L'Hopital's rule. The minus 1 is just there. That minus sign is just there. But the limit of this function, if you plug in and you get a ratio indeterminate, L'Hopital says that that limit is equal to another limit as t approaches negative infinity of you take the derivative of the numerator separate from the derivative of the denominator. Hopital says those two limits will be the same. Well, I can take the derivative of that. That's 1. I can take the derivative of e to the negative t. That is negative e to the negative t. Okay, fun. Now I think I'm trying this direct substitution again, plugging in negative infinity. Oh yeah. This time I just have that one issue. So negative infinity is positive infinity. This is e to the positive infinity, which is just infinity. This is 1 over a negative infinity, which is so small in this limiting process, we're going to call 0. I think negative 1 is my final answer. I've forgotten what we were even doing. I'm going to go back to my original question. My original question was to take this function and integrate it and basically calculate the area from negative infinity up to 0. I got a number, so that means my original integral converges, and when we add up all that area, we get negative 1. The negative area, that just means we've got a shaded region under the, below the x-axis. Wowza. Okay, I'm going to go through that again, just because I was confused a little bit. But I'm going to look at the graph real quick. Just make sure that makes any sort of sense. So I'm going to go back up to my monitor. I'm going to type in my original equation, which was x e to the x. Okay, yeah, it does have some weird funky stuff. I'm just going from negative infinity to 0. So I don't care about the stuff beyond 0. Just here. So yeah, there's this thin sliver of area. And then there's some good area right there. But this thin is clearly thin enough that it's not adding or diverging to negative infinity. It is getting so small that you're adding basically nothing. So it does sum up, and all this area sums up to negative 1. Or basically, the area is 1, but under the x-axis. Interesting. Very, very interesting. Okay, I'd like to just walk through that problem again. I was integrating this product. The negative infinity clued me in that I had to introduce a limit. I had to introduce a variable. Done. The integration wasn't that bad. It was parts, and it was quite nice. So I just quickly subbed that in. I had a little bit of dithering about how to plug in the t and the 0, but I eventually got down to something like this. And I had 2 limits. And the limit of a number just kind of is that number, so that negative 1 was there throughout. Oh, in fact, that was my answer, right? Negative 1. So eventually this other stuff just goes away. Okay. But I had to legally make it go away. All right. Here, I tried direct substitution, and I came across what we called a product indeterminate, which we don't know 0 times negative infinity. Sometimes it's 0, like in this case, but sometimes not. The way we handle that is we change our limit. Instead of taking the limit of a product, we take the limit of a ratio. And if that ratio comes out to be 0 over 0 or infinity over infinity, then we're allowed to apply L'Hopital's rule, which says you can go back to that limit, and that limit is equal to another limit. This is these 2 limits are not the same. It's a completely separate product. But whatever that limit is, it's going to be equal to this. So says L'Hopital. So now looking at a new limit, this limit, when I direct substitute, is doable. I get a number. It's going to 0. So I'm just going to end up with negative 1. That integral converges to negative 1. That puts everything together. You can see how we've just been building on our knowledge. You have to understand integration. You have to understand all the strategies we've been dealt with so far. You have to know that Calculus 1, how to handle the fundamental theorem of calculus, limits all that Calculus 1 stuff and just keeps building and building. That's why we practice and practice. Let's try another example. Change up the wording. You'll see this asked a lot. Determine if the integral from negative infinity to infinity of 1 over 1 plus x squared dx converges or diverges, and if it converges, what does it converge to? So if this thing diverges, well, it's going to infinity. But if it converges to some area, we want to calculate that area. Okay, this problem has some new stuff to it. Not only do I have one infinity, I've got two infinities. Oh dear. Okay, for a problem like this, I can't just plug in a dummy variable in the negative region and a dummy variable in the positive region and evaluate the two limits. That's not a guarantee. I can't just assume that that's going to be true. What I have to do here is separate this into two integrals, and I get to choose where I want to split it up. Like if 1 is a good number, I could use 1, sum up the area from negative infinity to 1, and then 1 to infinity. I think I'm going to use 0 here, just because zeros are typically easier to calculate. All right, so what I mean by that is the integral from negative infinity to infinity of this function, which should look familiar to you, is equal to the limit as t goes to negative infinity of the integral t up to 0 of this function, plus another limit as, I hate to use t again, but I'm going to. T approaches infinity of the same function, 1 over 1 plus x squared, from 1 to t. Basically, if you take the entire function and you split it up into two different portions and you add those together, that should be the whole function. Okay. And these two limits are doable because I only have the one variable to worry about. Okay, I'm going to limit the first one and the second one. This integration is extremely easy because that is the derivative of arctangent. So then the integral of this should be arctangent. Yeah. So same limit. I took care of the integration though, that is arctangent, but I do need to evaluate it from t to 0. To that, I'm going to add another limit as t approaches this time infinity of arctangent. This time I'm going from 0 to t. Before I apply the limit, I need to finish the calculus, and that is I need to finish that fundamental theorem of calculus, which says this integration process will be equal to that antiderivative plugging in the upper limit and subtracting the lower limit. So arctan 0 minus arctan of t plus the limit as t goes to a positive infinity of arctan of t minus arctan of 0. Yeah, I'm glad it chose 0. Okay, I know those values. Let me get a sketch of arctangent real quick. We restrict tangent to negative pi halves and pi halves. If those are asymptotes on tangent, they are asymptotes on arctangent. Tan of 0, 0, so then the inverse 0, 0. I got something like this going on. That's a graph of arctan. So I know arctan of 0 is 0. And in fact, well, let me just do this. I know arctan of 0, 0. I just plug that in. I think I'm ready for direct substitution. I'm going to plug in a negative infinity. Then here I'm going to plug in an infinity. I can look at the graph again for these values. Arctangent of negative infinity, well, that graph is approaching a negative pi halves. Arctangent of infinity is approaching a positive pi halves. So I have pi halves plus pi halves, that's 2 pi halves, or a nice pretty pi. That integral converges to pi. Sloppy. Therefore, that integral converges to pi. That's interesting number to add up to. You may want to plug that into Desmos, get a picture of that graph. No, I want to do it. I'm curious. I forget what these graphs look like. I'm going to go over and click on Desmos, and I'm going to plug in 1 over the sum of 1 and x squared. Yeah, if x is 0, I get 1. Okay, yeah, that shape is very familiar. It's that bell curve shape from like statistics. So it's very, very familiar, very similar. And come to find out, when you add those two areas, or you add the area over all that curve, it sums up to pi. How cool is that? Okay. Back to integrating, back to improper integrals. I have one more I'd like to talk about. And that is the integral from -2 up to 3 of 1 over x cubed dx. And it's the same question. I want to determine, does this converge or diverge? And if it does converge, well, what does it converge to? What does all that area sum up to? Now, at first glance, this may look like a p-test. I've got a 1 over x to some power. But for the p-test to work, you have to start in the positive region and go to infinity. So it's not the p-test. I just have one of those functions and I'm narrowing in from -2 to +3. Slice that, and then what's that area? Hopefully, though, you see a problem with this function. -2 is fine. 3 is totally legit. No infinities to worry about. What's my concern here? I'm on red alert, actually. I'm scared. I'm scared. Someone help me. This function has a discontinuity problem at what value? 0. And 0 is in this mix? Oh dear. That's a problem. So I only have one problem though, just that 0. So what I'm going to have to do is separate this integral into two pieces. I can go from -2 to 0, use a variable. Then I can go from 0 to 3 using a variable for that 0. What I mean the integral from -2 to 3 of this function is the same thing as the limit as t approaches 0 from the left of this function, of this integral marker. It's a big fancy integral symbol. That's what that is. From -2 up to 0 of this function plus the limit as t approaches 0 from the right of that same integral from 0 these are t's. No, oh my gosh. I'm about to scratch this all over and start all over, but no, I can do this. This is a t. Dang it. And this is a 3. Dang it. This is a t. Does that make sense what I'm trying to do? I've got this integral from -2 to 3. I got a problem at 0, so I'm splitting up the function. I'm looking at it from -2 to 0 and from 0 to 3. But 0 is a problem. I can't call it 0. I need to call it a variable t, and then I'm going to limit as I get closer and closer and closer to that 0 value. In the first one, I'll be approaching 0 from the left. In the second one, I'll be approaching 0 from the right. Sorry, but there you go. Okay. Now let's just do it. I'm going to take a look at this first one, and I'm going to do it. Let me underline in red the one I'm going to be looking at. And that's just a power rule. I can handle this. I like to rewrite the powers as powers. So 1 over x cubed is x to the -3rd. So then I know this will be, you increase it by 1, so -2nd power. Multiply out front by the reciprocal of that new power, -1/2. I need to evaluate this thing from -2 to t, and I still have a limit. Limit's still there. I integrated. I need to go from -2 to t. I think I'm ready for the evaluation process, that fundamental theorem of calculus. Oh, you know what? That -1/2 is a constant in a limit. I'm going to pull it all the way out. plug in the t, it's being raised to the negative second power, minus, plug in the negative 2, it's being raised to the negative second power. The negative powers, I'm going to rewrite those as denominators. Something like that. This is going to be a 1/4. If I plug in a 0 there, what does that mean? Evaluating my limit. 1 over 0 squared, where 0 is actually the smallest negative number you can think of, closest to this, yeah, minus 1/4. Okay, well, 1 over 0 is nonsense, but we're in this limiting process. So 1 over the smallest number, and it's even squared, so it's even smaller than you think it is. The smallest number is actually the biggest number you can think of. One over 0 is basically infinity. If you take a fourth away from infinity, and even half infinity, it's still going to be infinity. So that very first limit diverges. Well, if 1 will diverge, that means the entire thing has got to diverge. Even if I calculated this and it converged to 2, well, 2 plus infinity is still going to be infinity. So as soon as 1 diverges, you know the entire thing converges. That integral is divergent. It diverges up to infinity. So I wanted to show you this example for that hidden domain problem. Before, like all the integration I've given you so far has been pretty. It's been defined everywhere. So we could just focus on the strategies. Now that we have most of the strategies learned, we are going to have to start to worry about, well, where is the thing defined? So look for that. If you have a denominator, it can't be 0. If you've got square roots, well, there shouldn't be negative values. So look for that kind of stuff. I'm not going to tell you. I'm just going to give you this problem and say, oh, do it. So there you go. I think you're now ready to tackle the homework. Good luck, and see you in the next video.